So we're going to continue talking about systems of particles. Um, so imagine we have a set of three particles. Particle 1, particle 2, and particle 3. Okay? So our initial position, our initial center of mass is going to be somewhere, in the middle between those particles. And we know that our initial center of mass is going to be mass 1 times its position plus mass 2 times its position plus mass 3 times its position divided by the sum of the masses. But then let's say we're going to let the system evolve in time. And just like we talked about before, so we're going to look at some small amount of time dt. So that in that small amount of time, we're going to say that the velocity of none of these particles changes. In other words, there's a constant velocity in that amount of time. So if we look at that, we see that our first particle, we'll say, is moving up and to the left. Our second particle is moving to the right. And we'll also say that the third particle is moving to the right. Okay, so then at some later time, point 1 is going to have moved, point 2 will have moved, and point 3 will have moved. And so then we can also see that this also means that our center of mass will have moved. So our new center of mass, which we'll call R prime, is going to be equal to mass 1 times its new position plus mass 2 times its new position plus mass 3 times its new position, once again divided by the sum of the masses. And I may have done this before in this lecture series. If I haven't, notice that I put a prime here with each of these. I need some way to acknowledge that this is different than the initial position. Sometimes people put a subscript. I could have put initial here and final here, and then I would have an initial on each of these and a final on each one. I find a prime to be a little bit easier if I'm only talking about these two different times. So you'll just notice me using that notation from here on out in the class. But let's say now we want to find out what's this distance. What's the distance the center of mass has traveled in this small amount of time dt. So we'll call that distance dr center of mass, and that's going to be equal to r center of mass, the new center of mass, minus the old one, right? We talked about this when we were talking about adding and subtracting vectors. If you don't remember that, go back and look at some of the chapter 2 videos. So this is going to be mass 1 times the final R1 minus the initial R1, mass 2 and its difference in positions, and the same for mass 3. Can't quite fit it on the screen here. And we'll divide that by the total mass. But we see this is the same thing as mass 1 dr1 plus mass 2 dr2 plus mass 3 dr3 over m, where this would be dr1, this would be dr2, and this is dr3. So we can write the change in the center of mass as just basically the average of the change in the other positions. But now let's go through, let's multiply by the total mass, and then let's divide both sides by dt. So the small amount of time we're looking at. So now we say that m drcm dt is equal to m1 dr1 dt plus m2 dr2 dt plus m3 dr3 dt. Well, this should look familiar though. This is going to be the velocity of the center of mass. This is the velocity of mass 1, the velocity of mass 2, and the velocity of mass 3. In other words, the total momentum, so we can now say that the total momentum of the center of mass is the total mass times the velocity of the center of mass, and that's equal to the sum of all the other momenta. In other words, if we look at the total momentum of the system, that's also the momentum of the center of mass. So this becomes very important because now we can look at the entire system. Once again, like we saw that we can find its center of mass by looking at all the particles and averaging those together and acting like that's a single point. Well, not only that, but we can also talk about its momentum in the same way. We can find the momentum of the center of mass, and so if we have something like a baseball or a basketball or some other extended object, we're able to talk about its behavior just by looking at what the center of mass is doing without having to find out anything about all of the other particles that make up the system. And once again, this is going to be another thing that as we get further into the physics, this is going to become very useful for us.